Hello and welcome. In this video we're going to talk about the reflection and transmission of EM waves as they propagate from one medium to another medium. Now we've already looked a little bit at refraction, which was the flux lines, how they bend across an interface of two media. So this is not that. This is we're looking at the mathematical details of the waves, describing the waves in their mathematical details using cosines and sines. So how do those mathematical details change at the interface of two media? And also, we're in our class only going to consider normal incidence. So this means that the wave propagates head on to the boundary as opposed to some angle. So there is actually no refraction when that happens. There's reflection and there's transmission, just like maybe if you're in a car and you can look out the window, but you see yourself a little bit, so there's some light that's reflected from the glass, right? But also you can see outside, so there's some light that's transmitted through the glass. So there's some opaqueness happening there, and so that's what we're going to address here. How much of the wave is transmitted and how much of the wave is reflected? It depends on the characteristics of the two material, like air and glass. So let's check it out. Now, when a propagating EM wave meets an interface to a different medium, again, there's a transmitted and a reflected component. And we're only going to consider the simple case that the incident wave is normal or head-on to the interface. We will not, in this class, look at angled angled incidence. Now, the transmitted and reflected waves are going to depend on the permittivities and the permeabilities of the materials, as well as the conductivity. Now, suppose we're going to set up a situation that we've looked at before, where the z-axis is coming out towards us, or no, I guess let's make that the y-axis. Let's make that the y-axis. And so the z-axis is to the right, and the x-axis, the positive x-axis, is going up. And we're going to say that our wave is moving to the right. So this is our interface. Okay, so I guess before I draw the wave, let's just be concrete here, and we're going to say this is medium 1. Okay, so medium 1 is described by its permittivity, its permeability, and its conductivity. And then at z equals 0, then we have the interface, and then for z greater than 0, we have medium 2, and so medium 2 is going to be described by its permittivity, its permeability, and its conductivity. Now, suppose our wave is approaching, so I'm drawing that arrow right now, and so it's approaching the interface, and we're going to call that, we're going to use k to represent the direction of propagation. And so that's a k, a unit vector towards propagation. Here's the incident electric field. So remember, the electric field is perpendicular to the direction of propagation. So we're just going to say that it's up, positive x-axis. And from the right-hand rule, then that means necessarily that the magnetic component of this wave is coming out at us in the y direction. So this is our incident wave. Okay, and you'll notice that I'm using the subscripts I for incidence. So this thing is going to hit this boundary, and it's going to turn out that, as I said in the intro to this video, that some of the wave is transmitted. So if it's transmitted, then we would expect the direction of the electric component to be preserved, and of course it's going this way, right? And then the magnetic field is, as its direction is also preserved, so I'm using the subscripts T here. And so this is the transmitted wave. And just to give myself some space, I'm going to draw the reflected wave down here. Of course, it doesn't just jump down, but I just wanted some space. And actually, because of boundary conditions, the the electric field stays in the same direction, which is something that we talked about actually earlier in the course, the tangential part. And I'm not going to prove that the reflected wave is going to stay in the same direction, but you could. But so you just take my word for that. A little bit of hand waving there. But now it's reflected, so the reflected wave is traveling this way. And so that means from the right-hand rule that the magnetic field now goes into the page. So this is the reflected wave. And so the reflected wave, the magnetic field portion of this thing is discontinuous because it changes from out of the page to into the page. Good. Now, so we're supposing that the interface is at z equals 0, like I've shown here, and the incident wave is traveling in the positive z direction, and we're also assuming that the electric field is in the positive x direction. So we can write in phasor notation the incident wave is this. We'll say, or at least the electric field portion of this thing, EI0. It has some amplitude, right? And it might have some attenuation, and it has some wave number beta. Remember, gamma contains both of those pieces of information. The attenuation, gamma is the propagation constant, so it's got the alpha plus the J beta. It's got the attenuation constant plus the wave number. Then, if we're going to assume that that's the electric field, then we can write the magnetic portion, or the magnetic field, as this: the amplitude of E divided by the intrinsic impedance of the material 1, because that's the material that contains the incident wave. And so that is just this in the y direction, right? We reasoned through the directions already. And of course, this is a complex arithmetic here. So when I divide, the amplitude is going to get scaled, and the phase is also going to change as well. Now the reflected wave, so this is incidence. The reflected wave will look like this in phasor notation. So it will have some amplitude. It's going to possibly be different. That's what we want to figure out. How much is transmitted, how much is reflected. But we know that in the reflected wave, it's still going to go in the positive x direction, and the magnetic field then is going to go into the page, so it reverses direction, negative. And again, divided by eta 1, so this is a little bit of complex arithmetic. Okay, so we have this. And again, ER, reflected, and EI, incidence, has to be in the same direction to satisfy boundary conditions. So these are the reflected portions of the wave. Now let's describe the transmitted wave in the same way. So we've got the transmitted wave. I'll use T. It's got some amplitude. We don't know what it is yet. Okay, it has some propagation constant, gamma 2, and it's moving in the z direction, right? The wave, that is moving in the z direction. The electric field points to the x direction. And then the magnetic field, similarly, we're going to divide by eta 2 there because the transmitted wave is in material 2. That's the intrinsic impedance of the second medium. This is in the y direction, so this is the transmitted wave. And what we're trying to do is find out the relationship between the incident wave and the transmitted and reflected waves. Okay, so now let's look at the boundary conditions. And at the boundary, the tangential components of E and H must be continuous at the interface. So this is something that we talked about previously. And remember, the interface is at z equals 0. So it must be the case that EI0 plus ER0 equals ET0. So the incident amplitude of the electric field plus the reflected, because they're aligned in the same direction, equals the tangential. That should be obvious. And in terms of the magnetic field, this must be true. So these are H's, but I've decided to represent them in terms of the electric field. So this is the incident magnetic field minus the reflected magnetic field, because the magnetic field switches direction, equals the transmitted magnetic field. Okay, so now I can what do I want to do here? I can put E transmitted in for this guy here. All right, and that's going to give me one equation with just the incidence and the reflected. So we're just going to isolate the reflection right now. So when I do that, I have this 1 over a to 1, if I factor it out anyway, times this quantity here, equals 1 over a to 2. You know, if I arrange some things a little bit. Okay, so there's my equation with just the incident and the reflected waves. And again, if I do a little bit of rearranging, then I can get this as the following: 1 over a to 1 minus 1 over a to 2 equals the reflection 1 over a to 1 minus, or plus, excuse me, 1 over a to 2, like that. And again, if I divide now, actually, yeah, let me divide by this thing here. Okay, so then I would have the reflected amplitude, which is what I want, right? I want to do this for the reflection and the transmission. So the reflected amplitude is 1. It's this 1 over a to 1 minus 1 over a to 2 over 1 over a to 1 plus 1 over a to 2 times the incidence amplitude. Right? And I can clean this up even more. I can get a common denominator, and I can write this as, it turns out, a to 2 minus a to 1 over a to 2 plus a to 1 times the incident electric field. So what we see is that the reflected electric field amplitude is proportional to the incident electric field amplitude. And that constant of proportionality is this thing. It depends on the intrinsic impedance of the materials. And this thing here, this constant of proportionality, we're going to call that, or we're going to let capital gamma equal that thing. And capital gamma is what we call the reflection coefficient. And then we can write this equation in a neat form. We can just say the reflected amplitude equals the reflection coefficient times the incident amplitude, like that. Again, gamma is the reflection coefficient there. Now, let me erase this to the left, give me some space. And I could repeat this. Remember, we started with these two equations here based on the boundary conditions. And remember, I substituted ET in ET phone home I substituted ET in for this thing here, and that gave me an equation with just the reflection. I could alternatively substitute the reflection in for this thing here. Okay, and I'm going to let you do that on your own. And what you get once you do that, and once you use some algebra to clean things up a little bit, you get that the transmitted amplitude is twice eta 2 over eta 2 plus eta 1 times the incidence amplitude. So see if you can figure that one out. Again, you're gonna solve for the reflection in this equation and plug it in over there and clean it up. And so again, we see that the transmitted amplitude is proportional to the incident amplitude, and this is the constant of proportionality based on the intrinsic impedances again. And we're going to let the Greek letter tau, not to be confused with the time constant from circuits, we're going to let that thing be what's called the transmission coefficient, so that we can neatly write this relationship as ET0 is equal to the transmission coefficient times EI0, like that. Cool. Now, I just want to cover just one special case. Let's look at, I'm going to erase this up here to give me some space. Let's consider material 1. So this is the incident material. If material 1 is a perfect dielectric, so a perfect dielectric, if you recall, has a conductivity of 0, and let's say material 2 is a perfect conductor. And a perfect conductor, if you recall, has a conductance of infinity. Now, what would our transmission and reflection coefficients look like in that case? Okay, so I want to be clear, this definition of gamma down here, this is true in general, okay, and this definition of tau up here, that's true in general. Now I'm working on a specific case just to kind of gain some insight into these equations. Now, if you recall, the intrinsic impedance of a material is given by this, the square root of j omega mu over sigma plus j omega epsilon. Right? So right away we see material 2 with a conductivity of infinity. We've got a finite number over infinity, which is 0. So right away this implies that the impedance of material 2 is 0. Of course, because it's a perfect conductor, right? I mean, you can conduct or you can impede, but you can't do both if you're a perfect conductor, right? So right away then, if we plug in eta 2 is equal to 0 down here, we see that the reflection coefficient is -1 in this case, because we have negative eta 1 over positive eta 1. So -1. And if we plug in eta 2 equals 0 here, we see that we get a transmission coefficient of 0. So that's pretty cool. That means the electromagnetic wave is entirely reflected, that nothing is transmitted in the conductor as we would expect. By the way, why would we expect that? So here's my interface. Here's the perfect conductor. Here comes the EM wave. Why do we expect nothing to be transmitted here? Remember, no electric fields can exist inside a conductor. Perfect conductor, that is. So of course, there cannot be an EM wave in here. And amazingly, that's exactly what we see. A transmission coefficient of 0. Very cool. So now we can talk about the total electric field in material 1. So this is still in this case here. The electric field in material 1, speaking in terms of phasors, is is the incident phasor plus the reflected phasor, right? So we'll call that E1S, right? The total electric field in material 1 is made up of the incident magnetic electric field plus the reflected magnetic field electric field. All right, so I can rewrite that as E I0 e to the negative gamma 1 z. So that's the incident part. Then I have the reflected amplitude e to the positive gamma 1, because this thing is moving in the opposite direction. So we've got, remember, negative z moves to the right, positive z moves to the left. And the electric field we're saying is pointing in the x direction, like that. And so I can recall that gamma 1, sigma 1 is 0 in material 1. So that implies that alpha 1 is equal to 0. There's no loss in a perfect dielectric, right? And that means that gamma 1 is simply J beta 1. So now I can rewrite the total electric field, which I'm calling E1S, as negative E incident. So if I pull that out, then I have just e to the j beta 1 z minus e to the minus j beta 1 z, like this. And so I flipped these guys around. That's all I did there. And why is that? Or I guess what happened to the ER? Remember that ER is equal to the reflection coefficient times the incident, like this. So the reflection coefficient is -1. That's where a -1 comes from. I pulled that minus out, making that there. And the reason I pulled a minus out is because I want you to recall, maybe from signals and systems, that the sign of beta 1z, I'm just writing this off to the side right now because it's just a mathematical thing that we remember. The sign is related to these exponentials, like this. Okay? Remember the sign of theta is equal to 1/2 j e to the j theta minus 1/j2 e to the minus j theta. So I've got a sine wave here, which is interesting. So this makes minus j2 e I naught sine of beta 1z in the x direction. Now, if we convert back to time dependence from the phasor, so remember I've got E1 is equal to the real part of E1s e to the j omega t, right? The phasors. So this means that I would have 2 ei0 sine of beta 1z omega t ax. And you might ask, why is this a sine and not a cosine? Right? Because we're taking the real. Usually the real leads to a cosine. That's because of the j there. So the j now, right? Because we have cosine plus j sine, right? But when you multiply by j, it's the sine then that becomes the real part, and the cosine that becomes the imaginary part. Complex arithmetic. So this is what we get here. This is interesting. And again, this is the electric field in this case. All right. This is called, the result here is called a standing wave. And a standing wave does not move at all. It does not propagate. It stands still. And in this case, the incident and reflected waves are interfering with one another to make this wave that does not propagate. And just to show you how I know that this isn't propagating, well, you make some plots. Okay, so we were saying that our wave is moving in the z direction, so let's call that z, and the electric field is in the x direction. And so we know this is material 2, there's nothing here, and this is material 1. There's nothing that gets transmitted to material 2. Now, if I look at different times, right, because we want to see, is this wave traveling or not? If I look at different times, let's say t equals 0, right? Well, the sign of 0, oh, I missed something here. Let me back up. This is not correct. This is not correct. What I meant to write here is 2ei0 sine of beta 1z times the sine of omega t. Of course, you all caught that, and we're just yelling at the screen for me to fix that, of course. Okay, so now let's just plot the wave at different moments in time. So for t equals 0, this is sine of 0 is 0, so this whole thing is 0 at t equals 0. Nothing. Now at actually, I shouldn't have extended it in. I should just, yeah, like that. Now at let's say the period over 8, or yeah, the period over 8. So what you would see then is something that looks like this. Okay, for the period over 8. So remember, omega is 2 pi over t, and so if we plug in t over 8, then we would have pi over 4 here, and so I'll let you think about what that kind of plot looks like. And then if we plugged in t equals t over 4, what we would have is something like this. Okay, so this was t equals t over 8, and or t equals t over 8, and this is t equals t over 4, like this. And you can plug in other values of t, and you'll see something like this. You'll see something like this. Okay, so again, what's happening is the incident wave interferes with the reflected wave, and nothing gets into material 2, but what you have are these nodes. This is a standing wave, and these nodes are not moving, right? These are different values of time. Each plot here is a different value of time. So the wave moves kind of like this, right? It moves like this, but it's not moving this way or this way. So the wave is not propagating, it's standing still. And so that's what we mean by a standing wave. Very neat. So you get a standing wave in this particular example when material 1 is a perfect dielectric and material 2 is a perfect conductor. So I think that's all we have to say now about wave propagation, and we are going to move to next transmission lines. Almost there, last section, transmission lines. Thank you.